So, hi, eighth graders. This is the last lesson for week six. It's lesson 18. It's going to be really short. Like I mentioned at the beginning of the week, not a lot, really anything to do with this. I just want you to follow along with this, and then you'll have some optional work that you could do, or you could try to get caught up on some of the work you might be missing, okay? So hopefully you have a copy of this, or you can at least see it on a screen. And you also have your calculator. So the investigation is asking us to experiment with multiplying and dividing until we get a number that's not in standard form. So like if we are asked to use 2 billion by 3 billion, right? And we see it in the calculator here, and that's not standard form, right? Now, it does ask us to do this by hand. Now, this is a lot, right, to ask, but billion, millions, thousands, ones, right? So ones, thousands, millions, that's in the billions place. Times 3 billion, million, thousand. There we go. So multiplying this by hand would take a long time, right? But what if we just said 3 of these 2 billions? Okay, 3 2 billions would be 6 billion. Million, thousand, billion, million, thousand, yeah, wait a minute. And then what we would do is multiply it by the 1 million, okay? Now 1 million, since we've just been working with all of this, is really 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9th, right? One with 9 zeros after it. So I would take this 6 billion, million, thousand, multiply it by 10 to the 9th, which means I'm going to move it 9 more place values, or 9 more zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3. And so, geez, right? At this point, maybe you're thinking, well, I do know how to multiply scientific notation. It probably would have been easier to convert this to 2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. And multiply it by 3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. And since order doesn't matter in multiplication, I could do 2 times 3. And I could multiply my 10 to the 9th times 10 to the 9th. And hopefully I know that I just am going to add those exponents by that property we learned. And so we're just going to have 6 times 10 to the 18th power if we write it in scientific notation. Okay. Well, what is the connection then between this and what we're seeing right here? Okay. So why isn't the calculator showing us this? Well, pretty obvious, it's too big. But calculators aren't going to write things in scientific notation like this. It doesn't just automatically put in x's like this unless we're doing a graphing calculator and we're in a graphing function. So what it's going to do is give you part of the scientific notation, right? Those significant digits there is 6.0, a number that's greater than 1 but less than 10. And this is telling me the exponent on the power of 10. 10 to the positive 18. So that little e stands for the exponent on a power of 10, which is what we got right down here. Okay. Okay, this says to kind of play around with your calculator to see like how many digits yours has. You know, so all that's getting at is like, okay, well, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, Okay, that works with that many digits. So, and just playing around to see, well, when is it going to go over the top? Okay, let's add one more. Aha. So this just means I can display 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. This is 6 times 10 to the 10th power. So that's this digit and that many more zeros, so that's too many, right? So I'm only going to be able to show 10. Once I get beyond that, it's going to start writing in scientific notation, the calculator's version of scientific notation. So I'm going to turn this over. It's saying, well, let's multiply 2 billions by 3 billions, right? I'm just going to do that in my calculator instead of writing that out, okay? So, well, might as well do both, right? So, tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, right? And I know that's the same thing here with billions when in the 3 goes in the billions place, right? Well, let's just cut to the chase here, right? This is 2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, small numbers, so it's negative, times 3 to the, 3.0 times 10 to the negative 9, right? Now, let's just, if we point tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, now we're in the billions, times point tenths, hundreds, thousands, 10,000s, 100,000s place, millions place, 10 millions place, 100 millions place, now I'm in the billions place. And what do we predict we're going to get? And how do we predict it's going to look? There you go. So our calculator is giving us this notation. We know what it means is that we've done 2 times 3 and 10 to the negative 9 plus negative 9, which is 6 times 10 to the negative 18. So when we see this in our calculator, we can't just write this down as an answer. I know this for a fact when you get an algebra. If you write that down as an answer, you will get counted wrong because we have to interpret the calculator language. We have to translate the language of the calculator, which is 6e negative 18. 6 times 10 to the negative 18 power. This is the exponent on a power of 10. Okay? So if we just made something up right now, pretty big number, 2.3, 1, 2, 3, 4 times 3.4, 1, 2, 3, 4, 5, 6. Oh, I'm doing decimals. Sorry. 2, 3, 1, 2, 3, 4, 5, 6 times 3, 4, 1, 2, 3, 4, 5. 7.82e to the 13 just means, sorry, get that out of the way. Interpret, translate 7.82 times 10 to the 13 power, okay? So I'm gonna, this all came from your Big Ideas, so I'm gonna show you a couple problems from your Big Ideas book here and just see if you could figure out, well, what would we write for these if we came up with these? Just give me a second here. Calculator notation here, okay? So if we had 5.6e12 show up on the calculator, what is that translated to in scientific notation? 5.6 times 10 to the 12th power, exponent of 12 on a power of 10. 2.1 times 10 to the exponent of negative 10. And over here, we translate what the calculator displays into scientific notation, 8.73 times 10 to the power of, our exponent would be 16. So kind of important to know for next year. It's not something that we need to spend a lot of time practicing. So we're just going to leave it at that. Now, given that there was some more on the bottom of the paper that you printed out, though, I didn't want you to have thought, hey, I did all that work and I don't know if I got it right. So I just wanted to spend a minute and show you this just for grins. I don't know if you could tell that this was kind of like a microscopic picture. And so if all of these were the same unit of measurement of meters, well, the smallest would be here, right? So 10 to the negative 5 meters would probably be this microscopic picture. And then here we're pretty zoomed in, right? This is probably 10 to the negative 2, or 1 times 10 squared, or 1/100th of a meter, right? That's pretty close, 1/100th of a yardstick. Here, probably 10 to the negative 1, or 1 over 10 to the positive 1, or 1/10th of a meter away. And then we're probably looking at something like this. We can still see some detail here with the rocks and the leaves. This is probably a meter away, which is 10 to the 0, isn't it? 10 to the 0 is just anything to the 0 power is 1. So 1 meter. So we've got that one thing taken care of. And that leaves us with these, right? So 10 to the second meters, that's just 100. This looks like it'd be about 100 meters away, right? Whereas this is pretty distant, right? 10 to the 5th. Okay. 1, 2, 3, 4, 5. 100,000 meters probably makes sense for that distance, right? Okay, so like I said, the remainder of the items in the rest of the folder for lesson 18 are optional. If you are caught up, you do not need to do those. However, if you are not caught up, this is your chance because you are running out of time to get all that done, right? So do your best to try to get all that done, and remember that you need to email me and let me know when you do get some of that work done, okay? All right, best of luck to you.